So what I will talk about is about landscape triage, so a method to try to combine landscape ecology with restoration ecology. And this study was, we just finished this study, we submitted it 3 months ago. We still do not have a response from the journal, but it was developed by Daniele Rappaport, so it was a student that was in the lab in São Paulo, University of São Paulo, and now she is a PhD student at Yale University, and also Leandro Tambosi, former PhD student and now postdoc at our lab, and myself. Okay, so I will divide this presentation in 3 main topics. The first one, I will try to talk about extinction depth and what is the idea of extinction depth, and focusing especially on the Brazilian Atlantic forest. Then I will present this triage method that is commonly used in natural science, but I will try to do this transposition to the ecology science. And then combining these 2 first parts of the talk, I will talk about the landscape triage for the Brazilian Atlantic forest, and so how this triage can be useful to avoid extinction in the future. Okay, so we will move from Europe to another continent, to Brazil, and the Atlantic forest was the first forest that was deforested in Brazil. So it's not as big as the Amazonian forest, but it's a very rich forest, and it was where, in the coast, where the Portuguese arrived and began to deforest. So we have here in this orange, the original cover of the Atlantic forest, and in green, the distribution nowadays. So we have more or less 12 to 16% of remaining forest cover, and the problem is not only that we have too few forests, but also that those remaining forests are in very small fragments. So a lot of edge effect, a lot of effect from agriculture on those forests. So, and this is maybe of concern because the Atlantic forest is very rich and we have a lot of endemic species. So if we lose this forest, we will lose a lot of species. So for only if we consider birds, and we have data for other groups, but birds we have 1,000 species and 188 or around 200 species that are endemic of the Atlantic forest. So we are concerned about this deforestation, and if we consider the species-area relationship that was proposed by Arrhenius in 1921, if we lose 90% of the habitat, it would be expected to lose 50% of the species that depended exclusively on this forest. So, but at least from the data that we have, we lose, so 86%, 85%, but in the case of birds, we lose only 1 species. So, and it would be expected to have lost at least 100 species or something like that. So maybe the species-area relationship is not good. There are a lot of works that are reconsidering this relationship, but I think that the best explanation or the best hypothesis to explain why we are not losing yet so many species is that there is a delay between landscape changes and changes in the community. When we have landscape changes, fragmentation, deforestation, some species will reduce in abundance a long time, some will disappear after a period, but some will remain in the fragments for a long period, and this long period can be 100 years, can be even more. So, if we go in the fields, it would be expected that the number of species observed today would be smaller than the number of species that we have in the beginning of the fermentation. But even if we don't have any kind of changes, it will be expected that we will have some kind of decrease in the duration of the species. So I don't know if I'm really being clear, but there are species that are fated, that will be extincted through a relaxation process that occur, and then we will have some kind of equilibrium that is more or less predicted by the species-error relationship. So we have very good evidence that this is working. And the first evidence that I want to show to you is from a PhD student from our group. So here we are in São Paulo state, and we have here data from different fragments in the state of São Paulo. And we can see that for each of those fragments, we have the original species estimated by the species-error relationship, and we have the equilibrium regions estimated after this process of relaxation. And most of the observed species, number of species fragments, were just in between these two curves. So we lose some species, and we will lose other species if we don't do anything. And in some cases, when the quality of the forest is really bad, so there was degradation, the number of species today is even lower than the predicted by the species-error relationship. Okay, so we are in the process of losing species. We haven't lost everything, but we are in the process of losing species. So this is the first evidence. The second evidence is given several years ago by Brooks and Balfour, and they published in Nature in 1996. And they showed that for different regions in the Atlantic forest, in the Brazilian Atlantic forest, the number of predicted extinction considered this species-error relationship is very similar to the number of threatened species. So these species are there, and they will probably be lost if we don't do anything. And so there is a window of opportunity to act, and maybe the only action that will be promote the conservation of those species will be the restoration of the forest. Okay. So when extinction depths are more likely to occur? First, when deforestation is occurring very soon. So if deforestation occur in the past, probably time will be enough to pay this extinction debt. So first, extinction debt will occur when deforestation is in English just fast. But anyway, when we have very recent deforestation. Second, it's most likely that extinction debt will occur when we have an intermediate situation or an intermediate disturbance in the landscape. If the disturbance is too severe, as in this case, probably species will disappear immediately because we lose really all the habitat that support those species. And if the change is quite slight, not so important, maybe the species will support these conditions of disturbance, of small disturbance. So maybe what we expect at least is that extinction that will occur in an intermediate stage of disturbance. And third, extinction that probably will change according to the biological traits of each species. And in some case, if the species have a very long lived period, then like trees, for example, that adult trees can live more than 100 years. So the extinction debt will only be paid very in the future, very not immediately. And in the case where we have, as for example, for some small mammals that have a short-lived period, then this extinction debt should be paid very fast. Okay, so that is what the literature presents, and that the prediction that we can say about extinction debt. So, second part, I would like to talk about the triage method. So triage is a French word that would mean trier, So it's to sort. So it's a process of prioritization. So this is really used in the medical sense. It was used in the Second War, for example. It's used nowadays in emergency sectors of hospitals, in conditions where you receive a lot of patients at the same time, and you are not able to treat all the patients at the same time. You don't have any doctors, you don't have sufficient drugs to treat everybody at the same time. So you need to sort who will receive the treatment immediately and who will not receive this treatment immediately. So to do this kind of sorting in the medical sense, they use at least three main factors. First, the injury severity. Second, the consequence of delaying the treatment. And third, the probability that the patient will recover with and without treatment. And so, for example, if the injury is severe, and if you know previously that your treatment can help to recover the patient, and if you don't do this immediately, he will die. So you need to treat this person immediately. So it's 0 minutes. You need to really help this person immediately. But according to the situation, you can delay this treatment 10 minutes, 15 minutes, 120 minutes, and so on. So you have to decide who will receive the treatment immediately and who will not receive this treatment immediately. And in hospitals, they usually use these tags of different colors, showing that the red is really the urgent cases, and maybe the green or the blue one are those that they need to be treated, but maybe not immediately. And so there are very different kind of categorization and flow charts. So the medicals, they have this flow chart according to the respiration and to the pulse. And so they can decide if they will treat or not immediately. But what I like in this categorization here is that we not only have this red and to green tags, but we have also the black tags. That is the guy that arrived and is not breathing, is not pulsing, and so the guy is dead. So, and what is fine in this categorization is that you don't need to act in two extreme cases. When the patient is really in a bad mood, in a bad situation, and so you can't do anything and he will die. And when the patient is fine, and maybe you can even send the patient home, so he can treat himself at home and he don't need to be in an emergency sector of the hospital. So there are two situations, two extreme situations, where you don't need to do anything. And at this intermediate situation, yes, you need to sort people and to see who will receive more or less medical care. Well, 10 years ago, in 2003, Richard Hobbs and his Jensen, they adapt this triage method to the landscape situation. So using this kind of metaphor that our landscape are also not in a bad situation in several cases, and they need to be treated, and we don't have money to treat all the landscape at the same time. And doing this metaphor, Hobbs and Christensen, they consider two indicators. The first one is the level of threat of need of the patient, and the other one is the probability of recovery. And so according to this categorization that we have done, we have this matrix, and in this matrix maybe we can reclassify using these tags, this black tag, red tags, and green tags, for example, in situations as, for example, when you have a very high level of threat, but you can't do anything, your treatment is really not good enough to help this guy, so you can only give some palliative care, you can give him morphine or something like that. And in other cases, when the level of threat is low and independently of how good you can improve this situation, maybe you don't have to give a treatment immediately. But in some other cases, when the threat is high and when you have technology or when you have good treatments, you have to take some kind of emergency care. And so we can adapt this matrix to landscape management. So you can see in this slide different kind of management that you can do in this different situation, always consider the threat and the recovery capacity. So in some cases, for example, here that you just need to follow the transition of the system to a new situation. And in other cases that you don't have to do nothing or just protect or just isolate the area, but there are some situations where you can really do something and you need to do it immediately by a management intervention or by restoration. Okay, so this is really a fast presentation of the triage method, but now maybe the main part of my presentation is how we can adapt this landscape triage method to the case of the Atlantic forest. So I told you in the beginning that we have only 12 or 16% of forest left in the Atlantic forest. This represents 60 million hectares of forest, highly diverse and a lot of endemic species in this region. And by the new forest code, so this is the main law that acts on the protection of forest in private areas. So considering only the new Brazilian forest code that was accepted in 2012, we need to restore 6 million hectares of Atlantic forest. So it's a lot. Almost half we have to increase in 40% the cover of the forest in the whole Atlantic forest region. So we don't have, and this is really expensive. The median price of restoration is $5,000 per hectare. So if you multiply 6 million by $5,000, it's a lot of money. And we don't have so much, and so we have to have some kind of prioritization strategy. So what we proposed, and this was demanded by the Environmental Ministry of Brazil, so they demanded methodology to try to prioritize restoration areas in the Atlantic forest. So what we propose is to use this triage method that was adapted to the landscape context by Richard House and colleagues. So we want to use this considering basically two indicators that we call the urgency indicator, which is related to the level of threat, and the feasibility indicator that is related to the capacity that we have to recover the system. And the question is how we can measure these different urgency and feasibility. And so we proposed in this submitted manuscript a method that is based on calculating this urgency and feasibility indicator that are so inside the triage methodology. And we include a third component that we call a regional importance indicator. And then we use these three indicators to map and show which should be the areas that should receive the treatment immediately. So I will try to explain indicator by indicator and show some results for one region in Brazil. So this region is not a whole Atlantic forest, but it's an area, so quite a large area of 2 million hectares in the south of Bahia. I don't know how good you are in geography in Brazil, but it's in the Atlantic forest anyway, and we have a lot of forest there. It's more or less 30% of forest cover that we have in the region. But the most important is that we have very good data of landscape dynamic. And that's not always the case in Brazil, that you have with the same methodology and with a very good detailed legend and resolution. So we have this was prepared also by our lab. So we have very good data on the cover in the 1990s and in 2002. And so I will begin the presentation by the feasibility indicator, and then I will go to the urgency indicator. So we understand feasibility not only on the capacity that we have to recover the forest, but also on the cost-benefit analysis. So what we want is to the highest benefit when we compare changes, because forestry will regenerate anyway, but when we compare changes with and without treatment. And maybe the best theoretical framework that we have to deal with this situation is from a German group that you probably know, that worked with different kind of landscape that were more simple or more complex. And they showed that when those landscape went from more simple situation to a more complex situation without any kind of treatment, so natural regeneration, we improve biodiversity and we improve ecosystem service. But when we do some kind of management, the speed at least of this improvement is even higher. And most importantly here is to show that the effectiveness, so the balance between cost and benefit, is optimal at the intermediate situation. So when the system is too simple, maybe the cost is too high and the benefit is not really good. And when the system is really complex and really resilient, you don't need to do anything. The cost is not so high, it's not high at all, but the benefit is not good, so and by consequence, the cost benefit is not good. So the intermediate situation is when you have an optimization of the efficiency of your management. And this idea is very nice. So we try to adapt this to the Atlantic forest, and the question is, when is this window of optimization in management effectiveness? And so I'm more known as a fragmentation guy. I worked a lot in my PhD in France, and then afterwards, when I come back to Brazil, I worked more than 10 years working on the effect of fragmentation in the Atlantic forest. And we have so a 10-year database, very, very nice, and we recently did some synthesis of this data, and one of these syntheses was published recently in Science this year. And I think one of the most important results that we have from this project is that we show that consistently the community integrity of vertebrate groups, birds, small mammals and amphibians, so groups that have very different biological behavior, but they consistently decrease very fast below 30% of forest cover. So when you have between 100% and 30%, the community integrity is more or less good. So we have endemic species, we have some sensitive species, but below 30%, so you will lose a lot of species, the most important species for conservation. And so when you arrive in 10% forest cover landscape, you probably will have only communities composed by generalist species, and it's not what we really would like to have from a conservation point of view. And what we believe that is the mechanism that is generating this pattern is related to the landscape connectivity, to the biological fluxes that we have in the landscape. So when we have a lot of forest, the biological fluxes occur within, between, and along all the fragments. And the result is that independently of the patch size, you have communities with a large number of species, which is this solid line. And at the opposite situation, when you have only few forests left, those fragments will be too far away to allow biological fluxes between the fragments, then in this situation you have extinctions, and you have extinctions not only in the small fragments, but you have also through time extinctions in the large fragments, in the largest fragment of your landscape. So independently of the bed size, biological diversity will be low also in this situation. And at the intermediate situation, so you can have some situations, some landscape structure situations that allow biological flux and allow the maintenance of some species, more sensitive species, and the other situation no. So here you have a species-area relationship under higher diversity in situation where you can have larger patches or patches well connected. So this is really interesting because if we are right, the ecological resilience or the landscape resilience that we define as the capacity of the landscape to recover or to compensate extinction by recolonization is very high when you have a lot of fragments because those occur in the whole landscape. Decrease in an intermediate situation is very low when the cover in our case is around 10%. So very probably if you want to do a more effective management, you need to concentrate in this intermediate situation around 30% of forest cover. Because when you have a lot of forest, you don't need to do anything. The nature will do by itself, so the resilience is high, and so the benefit is not really good. And when you have few forest cover left, then it's really hard to, the cost of a restoration will be really high, and so the cost benefit is not good. So what we propose is that this window of opportunity to do really an effective management and probably a restoration management will be around this 30% of forest cover. So what we say, using again this triage tags, is that we have situation of high forest cover where you don't need to do anything, so it's green. We have situation where, maybe I'm really criticized by saying that, but situations that are lost, so maybe if we don't have money enough, we don't need to, we should not focus on these areas, but we have here a window quite large where we should act immediately to avoid extinction, the payment of extinction debt. Okay, and so maybe I need to, before saying exactly how we calculate the feasibility indicator, I need to explain what is landscape connectivity. So the classical definition of landscape connectivity is the capacity of the landscape to facilitate biological fluxes along the habitats. And obviously, this is dependent of some structural parameters as isolation and the distance between the fragment is related to the existence of facilitators, elements in the landscape as corridor of stepping stone, and will depend also on the permeability of the matrix of the land use area. But species do not respond to the landscape in the same way. So you can have a species that use corridor or that cross some large gaps, but other species will not use corridor or other species will not cross gaps between fragments. So they are not able to use the land use matrix area to disperse. And so if we really want to define landscape connectivity as the capacity of the landscape to facilitate biological fluxes, we need to consider not only the landscape structure, but we need also to consider the capacity of each species, so that will be species dependent, of using this element, of using corridor, of using stepping stone, of doing some gap crossing movement, and so on. So landscape connectivity is not an easy, it's quite easy to say what it is, but it's not easy really to measure if we consider biological fluxes as the center of the concept. Okay, But we have some methodology, some simplified methodology to measure landscape connectivity, and one of these methodologies is graph theory. So graph theory is a methodology to deal with networks. So it's used in different science, but in our case, this network is composed of fragments, of habitat fragments that are more or less distant from each other, and we can use very simple rules to say that even if those fragments are far away from each other, they could be functionally connected considering the biological capacity of movement of each species. So if we define a distant threshold, and if the distance between the fragments are below these distant thresholds, that will depend on each species, you can say that there is a link. But if the distance is above this threshold, there will be not a link, for example. So here we have a landscape, just to illustrate a landscape. It's the node, the center of the landscape. And we can say that there will be links represented by those arrows, and those links will depend on the capacity of the species to move. So if the species move 100 meters, 120 meters, so we have this kind of network. If the species move 500 meters, we have a much more complex and connected network. And so, this is another example shown as the same landscape can have different landscape connectivity, measured here by the graph theory. So here, for a species that move 750 and so on, so according to this distance, we have different networks. And what is nice to see here is that maybe these three fragments of the landscape are not important in this situation, but in this other situation, these three fragments are able to connect this large network in the north with this other large network in the south. So according to the species, we will find which are the best areas or the most important areas to conserve or to restore. Okay, very fast again. So we have indices based on the graph theory that are more simple and that consider only binary definition. They are linked. Fragments can be linked or not linked. For example, 1 and 2, these two fragments are linked, and 2 and 4 are not linked. So we can work with this 1 and 0, or we can go further and say that according, for example, to the distance between the fragments, you have a probability of connectivity. And so the simple model is based on distance, but you can include corridor, you can include a kind of matrix that is more resistant or not. But maybe the simplest way to measure and to measure this probability of connectivity is considering the distance. So, and then you have, or really do not want to bore you with mathematics or formulas, but this index is the best one according to what was published. So this probability of connectivity is a double sum of multiplication of attributes of two patches, patch E and patch G, multiplied by the probability of connection between those patches, and divided by the attribute of the whole landscape. And so we have, anyway, we have a very good connectivity measure based on the graph theory. And most importantly, the attribute here can be the area of the fragment, but can be anything else. Can be the population size, can be an ecological process, the intensity of an ecological process, can be anything that you think is important for your system. And so what we have done, we have, for the whole Atlantic forest, in this manuscript that was already published in 2000, so this year, in Restoration Ecology, we have done a first methodological proposal without considering time. And so the idea was to, we cannot compute the connectivity fragment by fragment, but we can compute the connectivity considering some landscapes. So we compute connectivity and forest cover for landscape of 5,000 hectares using this formula, the PC formula, and using biological data to shape this curve of distance and probability of connection. And so this is more or less the kind of results that we have. That's a very bad figure, that is the whole Atlantic forest, so more or less 20% of Brazil. And the red colors are the areas with higher connectivity, and the blue ones are with the lower connectivity. And if we plot, so all these landscapes here are represented by points here, so these 30,000 landscapes that we have in the whole Atlantic forest, according to the forest cover of these areas and the connectivity, you can see that there is a strong relationship between connectivity and forest cover. But for the same forest cover, you can have very different degrees of connectivity. So it's interesting to consider these two things at the same time. And we have very good data from the literature that say that when the forest cover is above 60% of forest cover, remaining forest cover, then biological fluxes are really fine and you don't need to care about those landscapes. And when the forest cover is between 40 and 60%, then you have to consider both forest cover and connectivity to decide when you need to have some kind of management or not. But anyway, the most important that I want to say here is that we can use forest cover and connectivity to try to define areas that should not receive immediate management, because the cost here is really high. Areas that we can only let the system act by itself, and the red areas that are the areas that need some kind of management and where the cost and benefit should be optimized. So basically what we consider in this manuscript is these two these two indices, the forest cover and the connectivity. And the higher the forest cover, the higher the connectivity, the more feasible will be the recovery of the forest. And maybe it's too many things to explain the same graph, but we divide our analysis in a restoration area and in a conservation area. So I will speak this, I will talk in this issue only about restoration. And so I will talk only on these gray and red areas. And so what we have done to define the feasibility indicator is to calculate the distance of each of our areas to the area with the maximum connectivity and cover within these two low resistance and intermediate resilience areas. And we have done some Z transformation to only standardize the values. Anyway, so the feasibility indicator related to cover and connectivity give us the capacity of the landscape to successfully support restoration action. Okay, so that was the P, and I will talk about the P now, the urgency indicator. So for the moment, we are not considering the dynamic, the temporal dimension. So we are not considering how the landscape structure changed through the years. And if we have these low resilience, intermediate resilience, and biodiversity sources nowadays, they can be the results of very different dynamics. For example, the intermediate resilience areas that I'm calling the areas the most important areas for restoration action, they can be originated by very rich areas, the biodiversity source in the past, or they can be originated in areas with very low emissions. And even if they are intermediate resilience today, according to this past dynamic, the importance of this intermediate resilience will be different. In this case, it's very probable that we will have a very high extinction rate in the red cases. And in the green cases, probably we will not have a high extinction level. So if we really are caring about avoiding the payment of extinction debt, we need to consider especially those landscapes that have loose forest in the past years. And if we see in our South Bahia region, I'll show it again. So here's the forest cover, here's the connectivity, and here for areas that has lost forest, and here for areas that gain forest. And we can see the size of the circle is related to how important was the change. And so you can see, for example, here that you have low resilience areas that do not change it in the past years, but we have here a large circle indicating that some landscape at least were highly deforested in the past. And so they probably were in the past or an intermediate resilience landscape or biodiversity source. And so this landscape is really an important landscape if we want to avoid extinction. So the urgency indicator was built in the way to identify those cases. And this is more or less a simple evaluation of how the area and the connectivity has changed in the past. The more we have change in the past, the more important and the higher will be the urgency indicator. Okay, so this is the urgency indicator. And finally, I will talk about this regional importance indicator and what is fine from this graph theory methodology. Sorry. Is that you can play in the computer. You can play as if you were a god, and so you can deforest it, or you can play restoring the landscape as you want. And what is fine is that when you deforest, you can measure the impact of this deforestation in the whole network. So for example, here we have a network with a PCs or landscape connectivity of 25. Don't worry about the unit. And if we remove this fragment, we will have now a network with a PC of 20. So we lose 4.3 of the PC value. So the importance of this fragment is 4.3. And so I can remove different fragments and see what is the impact of each fragment in the network, in the whole network. So I can do some kind of classification of importance of each fragment. Or, even more interesting if we are dealing with restoration, I can create new fragments in the landscape. And I can create new fragments that are situated in different locations. I can create fragments that have different sizes or different shapes. And I can see the impact of these different restoration simulation scenarios on the connectivity of the network. So it's very funny to play with the landscape once we have already the biological data to really calculate something that is meaningful. Okay, and so I can do the same with our landscape. So here we have south of Bahia. The green is the biodiversity source, so area that are okay. I don't want to act on those areas. But in green, we have this intermediate resilience landscape, and in gray, the low resilience landscape. And so I can play dilating all the forest in each of these landscapes, this hexagonal landscape, and see the impact of these individual landscapes on the whole network. So the capacity, the contribution of each of the landscape to really promote the connection between the biodiversity source areas. And so we did this. We did it systematically, considering different capacity of dispersion of species and integrating it in a multi-scale index. And And so we have this kind of figures that show in red here the areas that are more important for the in this regional context for the landscape connectivity, and in blues landscape that really will not contribute a lot for the whole landscape connectivity. And so now I have these three measures, these three indicators, and I can combine these three indicators or to define the restoration areas, considering the low resilience and the intermediate resilient landscape, or considering conservation areas in the biodiversity source landscape. But I will talk only about the restoration part of this methodology. So very fast, I'm finishing my talk. Very fast, show some results. The results by themselves, they are not so important for you, but just to illustrate what we have. So this is our landscape, South Bahia. So the forest is concentrated near the ocean here, and we have some corridors that go to the interior. And here you can see the biodiversity source in black, the intermediate resilience in green, in gray, and in orange, the low resilience landscape. So apparently there is a gradient from more connected landscape near the ocean and less connected landscape in the interior of the Bahia region. And so these are the results considering our three indicators: urgency, feasibility, regional importance. And you can see, looking only at these three results here, that an area that is important to avoid extinction, so the urgency, most important areas, are not always the ones that are more feasible. So, they are not always the areas that are more important considering the whole regional network. So we have different information. Here we show the areas that have more than 50%, that are the top areas for A, B, and C. Okay. And here I'm showing the results that we had before with the Leo Tambozzi paper. That are results that did not consider the temporal dimension. Okay. And maybe it's better to show you the comparison between the previous method that do not consider the dynamic with our three indicators. And what is clear here is that if you disconsider, if you don't consider at all the dynamic of the landscape, you probably will not be really effective to avoid extinction depth. So the urgency indicator is the one most related to the extinction depth, and you can see that independently of the urgency indicator, the analysis that do not consider the dynamic are really not good. So you can have areas that are really important here in the right of this graph, and that were classified before by us. We don't consider the temporal dimension as important or not important. But there is we have very similar results when we consider the feasibility indicator and the previous work. And the regional importance is exactly the same indicator, so it's 100% of fit. And what I think is more important is presented in this figure. So in this figure, I present the three indicators that we obtained. So the feasibility from the left to the right, the urgency indicator from the front to the bottom, increasing, and the regional importance in behind. And so you can see that, so the feasibility and the urgency indicator are the ones that are usually using the triage method. And this one is a new one, so and this regional importance can be replaced or combined with other indices, like, for example, the biodiversity impact, or if we are concerned with the cost, we can use an opportunity cost here. So we can have different other axes in this graph. But here we can see that according to the to what the manager wants to do in the landscape, we can have very different strategies. So if the manager wants to really have results, he will use the feasibility indicator and try to work on the landscape that are on the right of this graph. But if the manager is really concerned about avoiding extinction, so he needs to work on the landscape that are in the bottom of this graph. And if the managers want to work on landscape that will have a regional importance, so they have to consider the height of this graph. And they can combine these three indicators in very different form. So we are not here presenting the most important areas, but the green areas are the ones that perform well in the three indices. But the most important here is that according to the strategy or the task, the objective that each manager has, you can use these three information in very different ways. And this is what I think is really important triage method. The triage method say that really you have to concentrate resources in some conditions, but we have different kind of management action that can be done in the whole matrix presented by Richard Krauss and Christiansen. And that's exactly what we show here also. Well, just to finish, I'm talking here defending the triage methodology, but if you go to the literature, you can see that some authors, Stuart Pinn, Mittermeier, are really also really important persons in the conservation area. They consider that the triage method, when applied to conservation, will promote the defectism or is ethically pernicious in the way that you only concentrated in these moderately diverse and threatened areas, and that you do not give support for the best areas and for the worst areas. And so maybe, and I was really criticized presenting this in Brazil, that it's not possible to say that really landscape below 20% of forest cover does not deserve any kind of management. I have very long answer to this kind of criticism, but this is a kind of criticism that we have. But what I think it's important to say that this triage is a prioritization methodology that will be important only if we don't have enough resources. So only with it's 100% of the case usually. But this is a prioritization methodology, and I think it could be really useful. It's really used for medicine, and I think we can really use when we think about landscape management. So that's it. That's the place where I would like to leave. So I have a lot of students here, but what I think is really nice in the graph theory methodology is that you don't need so many data. And at this moment, the only data that I'm using is the gap capacity, the capacity of the species to cross gaps of different sizes. And this is an information that we got using radio telemetry, or using playbacks and stimulating gap crossing for different gap sizes. So it's a very basic information, and with this very basic information that you can get for some species in less than 1 year, so we have a data to parameterize this graph theory methodology. So if you want to use really other methodology that would require a lot of biological data, then I think we will be in trouble. But I think that the graph theory is just it's an intermediate situation, so it's a methodology that does not require a lot of biological data, and at the same time, it's not the opposite that you work only on the structure of the landscape. That is really common in Brazil, that you forget that there is function, that the function will change according to the species, though, so you work only with the structure. So distance, density of corridors, and things like that. So we are in this intermediate situation where we don't need so many biological data.
Okay, one more question.
If you look at the large temporal scales, you would see that also in your country you have fragmentation and coalescence of populations and forest land, for example, the Amazon. Very often you have for the those that were patches, let's say in the glacial maximum, you have the high biodiversity. So I would like to ask whether or not your fragmentation you see today in the Atlantic rainforest is correlated with the fragmentation you had historically. So it could become kind of confounding factor in analysis.
I do understand, but I think there are at least two approaches to read with this one. This question. The first one would be to have the data about fast fragmentation, and that's not always easy to get those data. But in another case, we can use biodiversity source areas and not structurally defined source areas that are used here. So it's the second approach. And there is, I think, a third approach is that instead of considering here an indicator of regional importance, we can use an indicator of biodiversity importance. And this biodiversity indicator, I think, synthesizes already the past history that generated this diversity. So I think that there is a different strategy to deal with this question that is very important.